So just like previously when we learned about subgroups and we learned about normal subgroups, we had tests that helped us show if something was a subgroup or something was a normal subgroup. We also have this for ideals. So Theorem 14.1 is the ideal test. And so it tells us what we need to do to show that the subset of a ring is an ideal. So let R be a ring and A be just a subset of R. Then A is an ideal of R if all of the following hold. So it has to be non-empty, just like with all the other ones. And then we have, for addition, we basically have the one-step subgroup test. So we have A minus B has to be in A whenever A and B are in A. So think one-step subgroup test for addition. And then in addition, we have this new property, this absorption property. And that says if you have an element A in A and an element R in R, then R times A is in A and A times R is in A. So A sucks anything inside of A. Let's look at a few examples just to get a feeling for what these things look like. So in example 2, we have a ring defined and then we have a subring defined. And so let's assume we already know it's a subring. So we don't have to deal with numbers 1 and 2. We just need to check if we have this additional absorption property. So what does part A look like? So our ring is the integers, and then A is all the multiples of 3. So A, let's list a few things. So we have -6, -3, 0, 3, 6, 9, and so on. So we have all the multiples of 3. Now, does that kind of suck things in this set? So we have to check for any R in Z and A in A, what does the product look like? Okay, so R is just an element in the ring, but A is an element in our subring right here. So we have that A has to be equal to a multiple of 3. So let's say it's equal to 3 times M for some M in Z. Then what does a product look like? So R times A is equal to A times R because we are in the integers right here. So we can do both of those together. And so A is 3 times M. R is just itself, but does it live in A? Well, yes, it does, because M and R are both integers, and so we have 3 times an integer. That is an element in A. And that's all we need to show that A is an ideal. So the answer is yes, it's an ideal. What about example part B? So we again have the integers, and here our subring only has the additive identity. It only has 0 in it. Okay, let's check again. So we need for any R in Z and any A in capital A, what do we have? Well, the only thing in A is 0, so we have A is equal to 0. And so we have A times R still equal to A, or again equal to R times A because we are in the integers. But R was something, don't know what it is. A is 0 though, and so this returns 0, which certainly, that's the only thing in A, so that's an A. And again, we have that A is an ideal. Okay, one more part. Let's look at C here. So now our ring is Z adjoint X. So those are polynomials with integer coefficients. And then A are constant polynomials. So A is, what's in there? Well, it's constant polynomials, but the constant have to be integers. So that's actually our integers. So we have, we can enumerate them. I'm going to start at -3, -2, -1, 0, 1, 2, 3, and so on. So let's see. What do you think? If we are taking something in the ring and we multiply by a constant polynomial, do we get a constant polynomial? That doesn't sound right, does it? No. So definitely doesn't sound right. We just need to find like one example of something in R that when we multiply by a constant polynomial isn't a constant polynomial, and that's not that hard to find. So we could take, for example, x squared. That is definitely in our ring. It's an element, it's a polynomial with integer coefficients, so that's in our ring. And let's take something in A, could be anything once in there. Let's take that. So if I take x squared and I multiply by 1, well, that's x squared. That is decidedly not a constant polynomial, so that is not in A. And so A is not an ideal actually is not an ideal in Z adjoint X.